Okay, hey, good morning everybody, and actually the talk I'm going to give is sort of circular because I'm going to talking about testing autonomous agents using autonomous test agents. Why the emphasis on autonomous agents? Well, I think in a short time we will be living in the land of autonomous agents. We see a number of examples of these agents in mobility, in the economy sector, in the services. So let's zoom into these examples and see what kind of benefits they promise to bring and also what kind of challenges they come with. So if we look at mobility, we have examples of self-driving cars, trains, and metro vehicles, in trucks. We also have companies studying how to make trucks autonomous and able to drive themselves. Drones are supposed to be used in a short time for delivery. If you look at the benefits that are promised by these systems, they include increased safety, so reduced number of collisions, better welfare, reduced labor cost, increased comfort, a better traffic, a higher capacity, and reduced congestion, and a better impact on the environment. If you look at the economy, well, algorithmic trading is already a reality. It's highly used by financial traders. More recently, we have seen smart contracts, which is sort of a novelty on the blockchain, in which you have these bots that operate on the blockchain and autonomously perform transactions that involve exchange of money and a lot of complicated stuff. So again, if you look at the benefits, there's a number of interesting opportunities there. These bots are going to be accurate, of course. They are programmed, they do not involve human emotions, possibly leading to irrational decisions. They can take advantage of data analytics quite extensively because they can automatically digest a huge amount of data. They come with lower costs, it's much cheaper to use a bot rather than humans to do these transactions. They can operate at very high speed and they can diversify investments. In the services area, customer services are being replaced by bots. You see examples of personal assistants that provide advices on gifts, on shopping, and in general on management of activities like the calendar and the music. So again, if you look at the opportunities and the benefits, people talk about increased availability. Of course, they are available 24 hours, 7 days a week. They can be very efficient, of course, in case the interaction with humans works fine. They come with reduced costs and possibly a higher customer satisfaction. So this is the sort of world that belongs to the land of autonomous agents. However, this world comes also with challenges. So what's going to be the safety when we talk about self-driving vehicles? What's going to be the reliability? So what happens when a failure happens in the field? Is the system going to recover quickly? What reliability is going to be delivered by these systems? Security, are these systems more or less exposed to attacks, to malicious hackers? And liability, we talked briefly about smart contracts. If a smart contract is implementing a fraud, who is liable? I mean, in this area, the smart contract is the law. There is no external law as a reference. So if you sign it, I mean, nobody's liable. You are frauded, and that's it. Usability, are we sure that these systems will interact with humans in a proper way? And these are open issues, I think. Just to look at these issues a little bit more deeply, this is a report that was published by IEEE Spectrum in February this year. The source is the California Department of Motor Vehicles, and it lists the number of disengagements of self-driving cars. So this means the car is driving, at some point something unrecognized or strange happens, and the car asks for the help of the human driver. And I mean, these numbers are a little bit worrying. Some are reasonably low, so 0 to 20 per 1,000 miles. Some are quite high. So we are not yet there, I think. Smart contracts. I mentioned the liability. This is an example. This contract that runs on the Ethereum blockchain implements a bank account. You can get the balance, you can push money into the balance, and you can close the balance. If the balance is closed, the contract sends the entire user balance to the user, and then the balance is closed by setting it to 0. Seems fine, apparently it is correct, but the real problem. The problem is that the function that is invoked to transfer the money to the user is this function value, can be actually redefined by the user and can recall withdraw balance. Since there is no protection from reentrancy, withdraw balance can be called twice. Okay? When it is called the second time, the balance is not yet 0. It is still the same amount, because it is set to 0 after the call to value is done. So the second call will find the balance, so it will try to transfer the balance to the same user. And the user gets the balance twice. This is a small example, but it's a summary of what happened in reality with the very famous DAO hacker that stole $60 million to the owner of a smart contract. So, and the owner had to pay, so who is liable? The contract has a reentrancy vulnerability. Who is liable for that? Nobody. The owner is signing the contract, the user is signing it, so the user can take advantage of this vulnerability. Here's another example of these challenges. So, if you're interested in the genetics of flying, maybe you want to buy The Making of a Fly, a book about these genetics. Actually, at some point in time, there were only 2 copies available. And one was sold by $1.7 million, the second copy by $2.1 million. So why this? The making of a fly, $2 million. The answer is algorithmic pricing. So both sellers were using automated agents to compute the price. And here is how the 2 algorithms work. One seller was applying a 1% discount over the minimum price. The other seller believed it was delivering high reliability, good services, so it was applying 27% extra cost over the average price. Since there were only 2 copies, minimum price and average were the same, of course, which caused, by the interaction between these 2 bots, an exponential increase of the price up to this point. And so, testing the individual bots is challenging, but when bots talk with each other, you can have these unexpected and unpredictable interactions.
Did anybody buy the book?
No, and actually the author was contacted and said, well, I don't think my book is worth this amount of time. Okay, so to sum up the challenges, the real problem with these systems is that today nobody knows how to effectively and efficiently ensure the quality. And the reason why nobody is able is because these systems come with a number of testing challenges. So let me go through them, and then I will give you some ideas on possible solutions. So first of all, in testing systems we are used to coverage. Coverage does not work well. We have seen it also in the previous talk. If you have a neural network in the system, you achieve 100% coverage in a single representative run, and you're done. That means nothing. So we need something else. Coverage is not enough. The input domain is huge. You can have images, speech, videos, natural language, huge number of environment conditions and settings, a combinatorial number of possibilities. So exploring this domain effectively is a big challenge. The world in which this system operates is uncertain. There's a lot of unpredictable variations that are very difficult to test exhaustively or in a representative way. And these systems are themselves very complex. They include complex technologies and they interact with complex frameworks, platforms, and other components. And they evolve at runtime. They can acquire knowledge, they can learn, which means that what you have tested in the lab can be different from what is actually running in the field. And for these systems, field testing is very expensive. So it's, if you want to test the real system, then you can do it only on a very limited number of cases. So the idea that I'm somehow trying to follow in facing these challenges is based on two notions. One notion is that since we cannot rely on coverage and the code as a reference, what we need is behavioral models. Behavioral models of the world, of the objects that populate the world, of the agents that can interact with the system in the world, and maybe also of the human. And a test case, a test scenario will be a set of instances of these models. So instances of the world, instances of the agents that are possibly running in a simulation environment where it's possible to execute more test cases. The second point is about the oracle. So with this systems, it's very difficult to say what's the input-output relation. Usually there is no predefined deterministic input-output relation that should hold. So to face this second challenge, one idea is to consider the behavioral goals of the system as the reference, and to try to derive quantitative utility or quality functions from these goals. And these become the test objectives that somehow replace the notion of coverage. So how can we achieve this? One possibility is using evolutionary optimization algorithms. These algorithms are quite promising in this area because they can capture the properties of these systems, they can adapt to them, and in general the idea is to use this algorithm to generate demanding test scenarios. What does it mean to generate demanding test scenarios? It means basically instantiating the behavioral models under the guidance of the utility quality functions. That's the overall idea. And then these algorithms can select and evolve the most demanding scenarios. So one example of these evolutionary algorithms is a genetic algorithm. I guess many of you already know it, but let me summarize it for those of you who do not. The key idea is that we can solve an optimization problem, which is represented by a fitness function, taking inspiration from natural evolution. And in this algorithm, we start with a randomly created population of candidate solutions. This is the initialization phase. Then these initial solutions are evaluated for fitness. So in my previous reference scenario, this fitness is related to the utility and quality functions. Then the best individuals are selected and are reproduced using genetic operators, typically mutation and crossover. The key decisions when applying these algorithms are how to represent a solution. This might be non-trivial in the case of autonomous agents and autonomous systems. There are several possibilities, bit vectors, arrays of values, and so on. What fitness functions to use? I already mentioned quality and utility functions, for instance, energy consumption, execution time, but you can imagine more. How to do selections? Here there are standard ways. Truncation, tournament, and non-dominated front, just to mention a few in the case of the single or multiple objective, and what genetic operators to use. These are usually mutation and crossover, but in the specific instances I will show you can change. Here is an example of application, a very simple one, just to give you a flavor of how this works. So we can start with an initial population of 5 individuals. These are also called chromosomes that are bit vectors consisting of 6 bits. Their fitness is evaluated and the best individuals are selected through tournament. This means we take pairs, we create a tournament between them, and the winner is selected. Here, for instance, the winner is this one because it has a double fitness. Then the selected individuals are crossed over, they are cut and their tail are swapped, and they are mutated. Here you can see. A simple example of mutation, which is bit mutation, bit flip mutation. So we have applied these ideas to the testing of an autonomous agent, which is an autonomous cleaner agent. The results are published in a paper that appeared in the Journal of Autonomous Agents and Multi-Agent Systems. The cleaner agent is an agent that implements a number of goals that are delegated by the stakeholder, like keeping the airport clean and doing it efficiently and robustly. It's possible to model the goals of this agent with a goal-oriented approach in which you have notions like hard goals, soft goals, goal decomposition, and contribution. Given this kind of representation of the goals of the system, it's possible to select the quality functions that we want to focus on during testing. So in this example, we consider two of the goals that we have here, which is maintaining battery and avoiding obstacles. You can choose more than two, you can choose whatever you want, depending on the objective, the purpose of testing. And then what we did was to use evolutionary algorithms to generate test scenarios where these quality levels are degraded, are poor. So if we take the evolutionary algorithm and the idea and we apply this scenario, well, the kind of solutions that we will be looking for will be instances of the world. Then once we have instances of the world, these are passed to the simulation environment where the agent operates, and at the end of the operation, we will collect quality function values. Then we will select the best individuals and we will reproduce them. Here the quality functions can be considered individually. In this case, we talk about single objective algorithms, which are quite different technically from the multi-objective ones, which involve, for instance, maintain battery and avoid obstacles at the same time. Yeah.
I have a question. To compute the fitness, you need a simulation of the physical.
Yes.
How do you call that? Is that a vacuum cleaner? What is it?
Yeah.
Yes.
Yes.
So you have a physical model.
Yes.
Yeah.
Okay, so what's the world model in this case? The world model consists of four elements, waste bins, so we assume we have two. So here we consider their coordinates. Charging stations, again we assume we have two. Obstacles, we assume we have a variable number, I know. And the vector that represents the model is the vector of the positions where we place obstacles. And the same for wastes. We assume we have NW wastes at the given positions. And we consider two kinds of cleaners. One is the simple cleaner, which has global knowledge about the environment, so it has this map. It's completely available. The second cleaner is an exploring cleaner that has only local information and it acquires knowledge about the environment as it goes. Both were implemented as JDX BDI agents. So if we go back to the idea of the evolutionary algorithm and we apply it to this scenario, well, the chromosome will be a sequence of floating point values that represent the coordinates of the charging stations, of the waste bins, of the obstacles, and of the waste. The fitness functions, since we are minimizing them, they are the inverse of the power consumption and number of obstacles encountered. So we applied evolutionary algorithms to this scenario, and first we observed that they can reduce over generations the fitness. So they can produce scenarios where power consumption is really high or the encountered obstacles are also increasing. It's possible to optimize or to minimize the two fitness functions individually, but also to optimize them at the same time using multi-objective algorithms. Here is an example of a word that was produced by minimizing the fitness function related to the obstacles. Here the cleaner agent starts at the lower left corner. So to increase the number of possible collisions, the evolutionary algorithms placed the black obstacles here because they are very near the waste bins and they obtrude the paths to the wastes. We minimize the other fitness function, the power consumption, and here it's interesting because to minimize it, the waste items are put at the corners so that the cleaner has to travel a lot before reaching them and then has to also go around the obstacles. We try to minimize both with a multi-objective algorithm, and here you can see that the wastes are at the corner, but the obstacles are also placed at proper positions such that the probability of collisions is maximized. So here, after taking this waste or this one, it can be quite challenging for the cleaner to go around the obstacle. And actually, this scenario led to the discovery of a real fault in the agent, which is related to the disabling of the avoid obstacle goal when the battery charge level is below 0.03. So when this happens, a collision can actually occur. But the collision requires two conditions. The battery level must be very low, and there must be nearby obstacles. So if you consider the single objective fitness functions, it's very difficult to find this kind of scenario. If you take both at the same time, this fault can be discovered. For the cleaner, we had similar results. Here you can see that over generations, it can increase the number of obstacles that are encountered and the power consumption. In terms of fault detection, if the fitness function is the obstacles encountered, the fault detection rate is quite high, but it is very low if you take the other fitness function. On the other hand, if you take both fitness functions, you can have a high fault detection, and at the same time, you can optimize all the testing objectives. So multi-objective was the multi-objective approach was very useful to find demanding test scenarios with a high fault detection power. Okay, let me check how much time I have. Oh, I think I have some time. So the second example I want to give you is about web testing. And in this scenario, we provided autonomy to the tester agent to explore web applications that are designed according to the modern design patterns for web applications, in particular the single page application patterns that support a very rich, let's say, execution environment on the client side, and also a very rich set of functionalities which can make these web applications potentially quite, let's say, intelligent and smart in terms of functionality. So the idea that we developed was to give autonomy to a crawler that is going to explore a single page application to support a reactive exploration of parts of the application that were not explored so far. This work has been presented this year at the Symposium on Search-Based Software Engineering. So the overall approach looks like this. We start from a static analysis of the application that provides us with a navigation graph that we want to cover. Usually this kind of analysis can be challenging. It becomes quite feasible if the testers have adopted a design pattern, which is the page object design pattern, that makes somehow explicit the set of navigation paths that are possible for the application. So we assume that we have this pattern and we can get a navigation graph. From this graph, we select the paths that we want to traverse, we select the input data, but then it might be the case that some of these attempts to navigate a path fail because the path cannot be navigated with the chosen data. So based on the measure of adequacy and feasibility that we collect when we try to navigate the paths, we adaptively choose a better set of data and a better set of paths. In particular, for data generation, we rely on EvoSuite, which is a very well-known and widely used platform for automatic test generation. And here the idea is that EvoSuite tries to fill the data values that are needed to explore the web application. EvoSuite tries to make the chosen path executable. If it succeeds, we use the feasibility information to create new paths that contain the feasible paths as prefixes. If it fails, we use the information on the infeasibility to try to avoid at runtime such paths. So in particular, what we did was to define new genetic operators that are integrated into EvoSuite that take into account feasibility and infeasibility and operate considering the structure of the navigation graph to select the paths that are more promising for the exploration of the web application. So if you consider the way the evolutionary algorithms work, in our case, a chromosome will consist of a sequence of navigation methods. So if you adopt the page object pattern, and navigations are represented through navigation methods. Here I'm omitting the data because, as I said, these are managed by EvoSuite with the standard genetic operators. So what we are interested in is a manipulation of the chromosome that selects the most promising paths for exploration of the web application. And in particular, we defined a couple of novel genetic operators, a new crossover and a new mutation operator that increase the chances of covering a part of the application that was unexplored so far. So for crossover, what we do is we take two chromosomes that are two sequences of navigation methods, we cut them, and we try to connect the head of the first with the tail of the second. This can be possible if the last navigation method in the head reaches a page that is also the same page that we have at the beginning of the tail. So at the beginning of the first navigation method of the tail of the second chromosome. If we are lucky and this happens, we can just take the two chromosomes, join them together, and we get a new valid chromosome for the exploration of the web application. If the tail is no matching, what we do is, first we check the reachability of the page from the last page that we have in the head of the chromosome. So if this head terminates with P4, we check if it is possible to reach P5, which is the starting page of the tail of the chromosome, from P4. If P5 is not reachable, we start deleting the final part of the head of the chromosome until we have a prefix from which it is possible to reach the page that we want to reach. And this is possible, we expand the chromosome with a random generated sequence of navigation methods. This is obtained through a random walk in the navigation graph, and then we can concatenate the two chromosomes. In the second example, if you take head 2, it terminates at P5. Here we assume that P4 is reachable from P5, so it's enough to just expand the chromosome and then to concatenate it with the tail of the other chromosome. For mutation, we apply deletion followed by insertion. We take the chromosome, we randomly select the navigation method to be deleted. Once the navigation method is deleted, we can have a mismatch between the target page of the previous method and the starting page of the next one. So we continue to delete successive methods until we find the matching page. At that point we stop. Of course, this would shrink a lot the chromosome, so we applied an insertion step in which the chromosome is expanded for a random walk to an unvisited part of the application. Okay, we applied this evolutionary approach to one case study, which is Adam's book. Here you can see some numbers about this application. And then we compared our tool SubWeb with Crojax, which is a state-of-the-art crawler for these applications. First, you can notice that the size of the graph that we consider, which is a statically collected graph, is much smaller than the graph considered by Crojax, which is a dynamically constructed one. So the dynamically obtained graph is much bigger. At the same time, it misses some of the transactions that we have in our statically collected graph because it was not able to explore these transitions. Now we consider the number of test cases that we generate in comparison with Crojax extended with the capability of test case generation. Since Crojax operates on a bigger graph, it produces also many more test cases. Moreover, Crojax fills in the data values of these test cases with random values, which means that sometimes it selects a path, but the values bring the application to another path. This is called a divergence, and here you can see that with Crojax you have a high percentage of divergent test cases. In our approach, since we do data generation and path generation at the same time through the evolutionary algorithm, we have zero divergences by construction. So this is the comparison in terms of test cases. In terms of coverage, here you can see the difference. We can cover much more of the navigations that are possible in the application, and the difference is statistically significant according to a statistical test. So in conclusion, our tool was able to produce a smaller navigation graph, smaller test suites with no divergent test cases by construction, and it was able to achieve a higher navigation coverage of the graph. So to conclude, my view is that we have to grant autonomy also to the test generators in order to deal with autonomous agents. I argue that test oracles will need to be replaced by quality functions that guide the creation of demanding test scenarios, and that in the end, the notion of test case will become quite immaterial. What you will have is an agent, like an autonomous crawler that is left there and operates and interacts with the environment until it finds some demanding scenario that is interesting for the testers. And I hope I have shown you that in at least a couple of cases, evolutionary algorithms are an interesting option to try to implement this vision for this system. So with this I conclude my talk, and thank you for your attention.
We have some time for comments or questions. There are obviously a lot of commonalities between this talk and the previous one, even though the vocabulary was not the same. So that's very interesting, but I don't want to be the one doing the talking. So. Anybody else? Where? Who?
I think that's
not okay.
Subway seems very, very interesting. Is it publicly available?
Not yet. We are trying to make it a little bit more solid, and then we will release it.
You may want to get closer to the microphone to answer the questions.
Actually, the answers will be recorded.
Okay. Yeah, Andreas?
If you say that in your conclusion, that instead of a test oracle that says correct or incorrect, we should have a quality function that tells us how close we get. How am I going to sell this to people in formal verification?
Is that an important question?
Let me assume that there are situations in which the devices, which is critical that the devices work 100% reliably. You want to come up with a proof of that. What is a 99%? What is the value of a 99% correct proof?
Yeah, so I would sell this to the formal people by telling them, well, you have a chatbot, and you want to know if it works as expected. You cannot say it is correct or it is not correct. It can achieve some quality of the interaction with the users, and you might be happy with the quality of the interaction or unhappy. So if we are talking about these aspects, I don't think the very notion of correctness is really applicable. I'm not saying this is true for every kind of system. This can also be complementary to formal methods in a way. But talking about autonomous systems to which we delegate some of the human-intensive tasks, I am in trouble with the notion of correctness. So in a way, I am asking the formal people their answer to what is a correct neural network that produces an answer that is given by a chatbot. Somebody.
To also provide another example to answer the question, you remember that in Sheila's talk, she was talking about automatic braking system.
Yeah.
And all those autonomous decision systems have limitations.
Yeah.
They cannot possibly properly react in any possible physical condition, and that doesn't exist. So then the question for that type of system is not whether they are correct or not, it's to understand what are their limitations. Exactly. Where do they start breaking down? Yeah. And so that's another possible way, yet another answer to the question, I think.
Definitely. Fully agree.
I think you intentionally put two very provocative statements on this.
Of course.
on this slide, of course, which raise these questions. Also for test cases, I would say if the system is very critical, you may want to always have a set of test cases that you want to be definitely correct. So eventually, of course, as we seem to all agree, there would be a hybrid solution in a way that you combine these two. But if I have a system that needs to shut down if X and Y and Z happen, I don't want to rely on an agent. I want to always test this case as well, and also return it.
Yeah, no, I fully agree. I was intentionally provocative, but I think that in this, let's say, provocative claim, there is somehow a stimulus to think differently, because in the testing community we are used really to think of test cases, coverage, these kind of notions. And the notion of a test agent or a word creator that produces demanding scenarios is something relatively new, I mean.
But if you're talking about autonomous systems that have complex interaction with the physical world, and the number of possible scenarios in the physical world is, infinite. There are many more and more examples of such systems. Guaranteeing a behavior in any possible condition is not going to be achievable with formal methods. The formal methods themselves break down. So then, but you see, you cannot even answer that question with existing techniques. And actually, that's what Shia was trying to convey in your last slides. Regarding model checking, but she could have taken other examples. Then, in any case, formal methods don't solve the problem. For that type of autonomous system we're talking about, the ones that are more and more common. Of course, if you have a shutdown operation in a nuclear plant with very limited conditions, there are 3 sensors and there are 15 scenarios that can happen. But then here, in that case, I was going to show you need a formal method. Basically, you run exhaustively on the scenario. So you see, you have a spectrum. You have, on one extreme, you have a very limited number of scenarios and you need certainty. And here you maybe need formal method, just do some kind of exhaustive testing. At the other extreme, you have an infinite number of scenarios in a very complicated physical world. And here, those formal methods don't really work. So maybe they work somewhere in the middle. And they work somewhere in the middle when there is no physical, when there is no dynamic behavior involved.
I agree with you, but I don't know if I'm seeing it perfectly well, but I think even in a very large system with different, you may still have conditions that you want your system to behave no matter what. So, for example, autonomous vehicles, again, they are very interesting examples for me because they combine many things that we look at. So there, for example, if you have a, gas leak sensor, let's say, before they all become electric. You don't want to start the engine or you don't want to operate the machine. So you don't want to rely on an agent to test different cases. Like this is different from how you drive the vehicle. There are certain things that you want always be respected regardless of the situation.
No, that is true. I fully agree. Still, if you consider some aspects of the behaviors of these autonomous systems, I think they challenge formal methods that become basically inapplicable. And I mean, going back to the circularity of my talk, I think that evolutionary approaches or AI-based approaches in general have the kind of flexibility and adaptivity that is needed to put in the field or put in the simulator a test agent that can produce interesting scenarios.
Only on test cases.
So, to summarize, I see a lot of commonalities with the previous talk, and actually I knew that. That's why I put two talks together. It wasn't chance. Basically, you are trying in a very large input space to find worst-case scenarios, which are defined according to a fitness function. And that's also what we did, but in a different context. It requires physical modeling to compute the fitness function. It requires to model whatever is the thing that you're controlling. your vacuum cleaner or whatever it is, or your call for the contract. I'm not too sure how to make the analogy. But
Well, probably you can simulate the transactions of a smart contract in a local blockchain. That's easier in a way because it's not a cyber physical
it's not
system.
physical, yes.
I mean, so if you have chatbots or financial bots, it's easier
Yes.
and
So
faster.
you do that, but then you had a challenge at the very beginning of your talk that seems to make things even more difficult. And then I don't know to which extent this is good enough to address that challenge. You talked about, of course, those autonomous systems that are learning as they go, and whose behavior is changing as they go. Then how does that impact? Because here, none of the examples you have are changing.
No, that's true.
You know, as
So first.
What do you think? I know probably you'll have a definite answer, but what is your...
No, right. It's a big challenge, and I have also to say as a disclaimer that the two works that I presented are very preliminary in comparison with the vision. So initially, I gave you a sort of a vision of what I would like to do in the future, but I did just a little part of it. In a way, if you can simulate learning, then you can have the evolutionary algorithm that is co-evolving, and that could be an answer. I know it's a partial answer because, I mean, if it is already difficult and costly to do simulations without learning, if you introduce learning into the picture, then, I mean, the space of possibilities is even bigger. Another possible answer is field testing, or online testing. So we probably, with these systems, we probably don't have a chance to do all the testing offline and in the lab. We have somehow to draw a connection between what's happening in the field. We need ways to monitor and to collect data to somehow focus testing on the scenarios where there was some learning or some knowledge acquisition. But I agree, it's an open challenge.
Thank you. Is there a last question before we break for lunch? Yes, correct.
How do we test the destinations?
Yeah.
Just for fun.
Yeah, it makes a lot of sense. I claimed it was circular, so this answer makes a lot of sense. But I mean, in reality, you don't need to test it. I mean, as long as it finds faults, you are happy, even if it has bugs in a way. That's the easy answer. On the other hand, no, it's true. You probably have to apply testing techniques also at the meta levels.
Can use the test agents to test the test
Yeah.
agents.
This is really the very last one.
Yeah, it's interesting, kind of obvious, but in some sense, evolutionary, as many AI are kind of like approximate computations. So in a sense, they solve this problem by themselves. I mean, actually, the fitness functions is what you need to test here, right? So, and that's they are so simple in some sort of way. You know, you can check them on the paper. I think it probably we have something to learn for the runtime application of AI. They could give more robust systems by themselves. Because they don't rely on exactly this value here and there.
Comment was sort of a joke on the idea, but at the same time philosophically, so I see it this way. We look at an AI system and we think it's very complex. We may not know how it's behaving, so we may not know what are the maybe rare situations in which it does something wrong. And now if we use another AI autonomous agent to test this, we sort of defer the problem to the layer. Because what if that machine also decides that certain conditions that for us will be important are not important?
No, that's true.
So of course your fitness function helps, but still,
No, it's true.
There is this, we hide away
No, that's true, but in a way, the problem that you face is mostly with the missed alarms. Because if you get an alarm from the system, if you get a demanding scenario, that's useful. Even if it is produced by a buggy system, you don't care. You could miss alarms, and then that becomes the problem. But as Robert said, in the end, the critical part is the fitness. So if you design it carefully, and it's reasonably fine.
If the test, or what you call the test agent, we do the same thing, we don't call it that way. is somehow buggy, that this is imperfect, it will just make the test generation less effective.
Yeah.
But it won't have any
Exactly.
other impact, just like your testing is. And actually, when you do the big empirical studies you need to do when you design such algorithms, there is no way around. If the bugs are really severe, you will see it, because it will work. It will do worse than random testing.
Yeah.
So you will see right away there's something wrong. And, it has happened to us with Shiva, and I'm sure you have the same experiences. There is a bug somewhere, and you do an experiment, and you realize you are doing worse than the C+ algorithms. And then, this is due to a bug somewhere.